In this video, we're going to talk about the relationship between expected value and simulation. The nice thing about simulation is it's a way to, I always say it's a way to replace the math. So when you take statistics and probability, especially if you go on to take more than just an introductory level statistics course, you're going to discover all these different rules about probability. You're going to learn about conditional probability. You're going to learn about the multiplication rule of probability, all these different ways to figure out the likelihood an event occurs um, given certain percentages and probabilities. Now, the thing I like about those rules, multiplication rule, the conditional probabilities, all of those things, the thing I like about it is the fact that it gives you a clear cut, accurate theoretical probability. Okay, the thing I don't like about it is sometimes it's difficult for students to understand how to get that percentage when the answer is right in front of them, and they can come up with an experimental probability that may not be the same as the theoretical probability, but it's pretty darn close and it's a lot easier to get to. Okay, it kind of reminds me of a scene from Austin Powers. If you've seen the movie, when Doctor Evil captures Austin Powers, and he has this whole tank of piranhas set up, and he's going to try and get Austin Powers to be in that tank, and the piranhas will eventually kill him. And his son Scott comes down, who isn't in agreement with his father too often, and he says, "Dad, I have a gun in my room. Why don't we just go kill him?" And the bluntness of that statement, and it's funny as you watch the movie. That's kind of, I think of that action as like the experimental probability, and sometimes Austin Powers being in the piranha tank, so to speak, this whole laborious concept of figuring out theoretical probability and going through these mathematical models and rules to get to an answer that, hey, it's right underneath my nose. I can just simulate the event. I can just go do it, and I can see what I get. So I'm going to show you that method here of simulating an actual game that you may see in a casino in a few short years. So enough movie talk. Let's get to the actual problem here. So, okay, we have an American roulette wheel, has 38 slots, 18 are black, 18 are red, and 2 are green. When the wheel is spun, the ball is likely to come out to any rest in the slot. So you can see over here, we have a roulette wheel to our left. Okay, and basically how it works is the dealer will spin a little white ball. This this will spin on its axis, and then it'll land in one of these spots. And if you put your chips on one of the spots, you're going to win some money. So a couple ways you can play. You can put your chips on a single number. You can put your chips on these sections down here, like 1 to 12, 13 to 24. You could also put on red or black, even or odd. You can do what's called a column bet, which is what we're going to look at in this example, okay, which is a 2-to-1 payout. As we can imagine, the red to black, or red and black payouts would be 1-to-1. Same thing with 1 to 18. Okay, so let's say in this example, we are deciding to put our chips, or our $1 chip, we'll say, we want to put it on a certain column. Okay, we want to figure out what the expected payout is going to be. Okay, so for the time being, here's what I'm going to say. I'm going to say our $1 chip, okay, and we're going to just say this guy is equal to $1, okay? A blue chip is equal to $1, and I'm going to put that blue chip right here, okay, on the lower. And I know it sounds odd. You're like thinking, well, column bet, that doesn't make any sense. It's a row, but they call it a column bet. I guess if you're down here and you're facing the wheel this way, it would look like a column, okay. But for right now, we're going to call that a column bet, and we've spent $1 on it, okay. And basically, if I get a 1, a 4, 7, 10, 13, 16, 19, 22, 25, 28, 31, or 34, I win $3. Okay, we want to figure out what the expected amount we win is. In other words, taking into account the likelihood of all the others, what's the likelihood I win? Okay, so we're going to come up with a probability model first so we can do our expected value correctly. So the way I look at this thing, you're either going to win or you're going to lose. Okay, and in both of these events, we're going to have a payout, and we're going to have a probability. Now, the probability, I think, is going to be the more difficult variable to figure out, but we can do it. Okay, so here's our little, we're gonna make a little table here. All right, we either win or we lose. Okay, there's no in between, right? So to win on a column bet, just like I said, we're gonna win $3. So the payout is 3. If we lose, we get nothing, right? That makes sense. So what's the likelihood that I win in this case? Okay, well, I just rattled off the numbers that would win. I just want to count up how many of those there are. And then here's the key. We have 38 slots in the roulette wheel. Okay, these green spots, the 0 and the double 0, okay, this is not included in any column bet, in any red or black bet, or any 1 to 12 bet, or any even or odd bet. And that's really what makes the house money, is because it keeps we'll call it a 50-50 or a 1-to-1 event from being a payout of truly 1-to-1. Okay, so the probability of a column bet here, again, let's count them up. I have 1, 4, 7, 3, 4, and then 4 in this section, 4 in this section. I have 12 ways to win, and then I have 38 different options. So the probability of success, in theory, we might think, okay, it's 1 out of 3. It's going to be a little bit less than 1 out of 3. Okay, and then all the other possibilities of me losing. Okay, in this case, I have the difference. And honestly, it doesn't matter, but we'll list it for now, right? Because it's just going to be multiplied by 0. So I have 26 other slots that this thing can go into, right? I have 12 up here, 12 up here. That gives me 24. And then the 2 zeros would be 26. So 26 out of 38. Okay, that's my probability model. I haven't gotten decimals yet. We'll get to that in a second. Okay, but what my expected value would look like is, again, we're just going to multiply the probability by the actual dollar amount. Okay, so for the first one, we're going to get 12 out of 38 multiplied by $3. And then the next one, we're going to do 26 out of 38 multiplied by $0. Okay, and again, like I said, that's just going to cancel out, right? This is just going to be 0. And then 12 out of 38. Now, I could get a decimal, but I'm going to treat this as multiplying by fractions. So 12 times 3 would give me 36, all over 38. And if I get this decimal amount, we're going to do 36 divided by 38. Divided by 38. And I get roughly 95 cents. Okay, so my expected payout, in other words, every time I play the game, in the long run, I'm going to win 95 cents every time I spend $1. Okay, I'm going to write that dollar amount right next to that expected payout, okay, because that's, I think, the telling piece in why the casino makes money. Okay, it's a very small amount, right? It's only just a difference, okay? But in the long run, every time somebody spends $1 on the roulette table on this significant bet, as lucky as they may feel, as good as they may feel, they are going to lose 5 cents every single spin for every single $1 bet. So that's why the house will always win, because even though I spend $1, I'm expecting in return 95 cents. Okay, it sounds kind of silly when you think about it, right? It's like if I were to buy a stock and I know that whatever the price of that stock is that I bought, when I retire, it's going to go down. 100% it's going to go down. Yet I still put money into it. That's why playing at the casino is such a dumb thing to do. Okay, now let's say I totally forgot about expected value. This is where simulation comes into play. Okay, how could I simulate this event and try and figure out an expected value of 95 cents? Okay, to some it may seem like it's a little more elaborate, okay, but we're going to try and show you here. Okay, so think of it this way. Let's remodel every single game as a winner, right? So the 12 numbers that would win are, we're going to highlight in, let's do this. Let's actually highlight this in yellow, right? And I'm going to highlight on my grid up here, if you can follow, all of those winners, okay? All of those winners are yellow. Now let's highlight the losers. We'll say the losers are going to be in blue. Okay, what numbers are going to lose? So I have all these up here. I have all these guys up here. Okay, and then don't forget our double zeros, okay, over to the side. Okay, so now if I don't have the means to a roulette table, which hopefully most of us don't have, I do have this little thing called random.org, okay, which can simulate numbers from 0 up to 36, or 0 up to 36. We'll get to that in a minute. And I can simulate this game totally randomly, okay? So let's say, and to get a good solid sample size, let's say I'm going to play this game. We're going to play the game 50 times. So in a minute here, we're going to randomly draw 50 numbers from 0 to 36. Okay, and we're going to see how many of them are either 1, 4, 7, 10, 13, so on and so forth. And then we're just going to figure out the probability of that and then come up with an expected value. Okay, so here's the problem. If I go to my website, and let's actually go over to random.org just to show you how this thing works. So if you go on to random.org, you go over here to the bottom right, there should be a dialog box for a true random number generator. And you can change these numbers to anything. So in this case, I might want to go from 0 to 36, right? Problem is, I haven't taken into account that double zero spot, right? There's no way to go 0, 0, 0, 1, 2, 3. The computer's not going to do that. So here's what I'm going to do. We're going to go from 0 to 37, and we're just going to understand that, and I'll write it over here. We even write like a little number 37. Okay, if I get 37, that's going to represent double zero. Okay, and we're going to do 50 times, and we're going to see what numbers we get. Okay, so the first one, we're going to click on generate, and I got a 1. Okay, so the first game I got a 1, so the first game is a win. So I'm just going to list this as a win. Now you're going to see this list may get a little hectic, but I'm going to show you a quicker way to do it too. Okay, second number was a 9. Okay, number 9, where did that go? Okay, that's over here. So second game is a loss. Let's do it again. Next number is an 18. All right, 18 is up here. That's another loss. Now, if I want to keep going on and on, hopefully you get the idea. 47 more times and writing out win, loss, loss, win, loss, like that's going to take forever. So here's what I'm going to do. We're going to keep these as our first 3 events. Go back to random.org, and I want you to go to numbers, integers, and there's going to be a way that we can simulate 47 more games in the click of one button. So we're going to generate 47 random integers between 0 and, again, 37. And we can format that. This is totally a personal preference. Let's just say we leave it in 5 columns. All right, they both are inclusive. And if we click on Get Numbers, we'll get those numbers. Okay, sometimes you see a repeat, like I see 0 3 times already. Okay, now, and it just, again, lists out every single event. Okay, so I want to go through this list. And again, the only numbers I'm looking for are 1 and then adding 3 consecutively. So 1, 4, 7, 10, 13, 16, 19, 22, 25, 28, 31. Anytime I see any of those numbers up to 34, okay, we're going to say that it's a win. Everything else is a loss. So I'm assuming there's going to be more losses than wins. So it's easier to count off the wins because it's going to be a lower set. Okay, so let's try and highlight them. Okay, 7 is definitely a win. All right, and I'm just going to keep a tally over here. All right, let's say let's use these both as like kind of tally charts. So for my wins, we're going to include this one right here. For losses, we're going to include these 2. All right, and then the 7 was a win. And let's just go right down the row here. 23 was not on that list. 37 is a double zero. That doesn't work. Let's see, 14 was not on that list. 18 not on that list. 25 is on that list, so that's a win. 32 I don't believe is on that list. 35 not on the list. 17 is not on the list. Okay, so in the first column, the only winners we have are 25 and 7. Let's go to the next one. 3 not on the list is 12 not on the list. 23 not on the list. 34 is on the list, so that's another win. 7, I believe, was on the list. Yes, sir. So that's a win. 9, was that on the list? Nope. 19. I don't believe, oh, 19 is on the list. Okay, so we're up to 6 wins. 0, not on the list. 17, I don't believe is on the list. 30, again, is not on the list. Okay, so halfway, almost halfway, we've got a couple wins here. Okay, so 7 and 1, I believe, are both on the list. So we're going to chalk up 2 more wins. 1, 2. 10, I don't believe. No, I'm sorry, 10 is on the list. 15, not on the list. Is 19 on the list? 19 is on the list. Okay. Is 12 on the list? 12, no, sir. 4, is 4 on the list? Yes, it is. Is 12 on the list? Nope. 27, not on the list. Let's go over to this column. 24, not on the list. 12, not on the list. 0, not on the list. 36, I don't think is on the list. 17, nope. 17 on the list. 10, again, is on the list, so we're going to chalk that up. 10 is another win. 17, no. 0, no. 2, no. Let's go over here. 34 is on the list. I believe correct. 34, 31 is on the list as well. 0, not on the list. 13, 17, 13 is, 17 is not. 27 is not. Is 13 on the list? Yes, it is. 25 is on the list. Okay. And last but not least, 18. 18 is not on the list. Okay. Now, I only kept tallies, for the wins. For the losses, that list would just be too long. So we're just going to do a little bit of math to figure out what that's going to be. So we have, let's see, 5, 10, 15. We had 17 wins, and the rest would have been losses, right? 33. Okay, so my experimental probability here, my theoretical probability of winning was 12 over 38. Okay, and I'm going to actually circle this from our previous example, and we're going to call that theoretical. Okay, that's our Austin Powers in the piranha tank. This experimental is us going up to the room and getting our gun. Okay, now it does seem like it took a longer process. You're probably thinking, like, what is he talking about here? This took such a while. And it did, but when you think about, did we have to really do any math? Not a lot. We just have to remember to figure out the likelihood that we're going to win. So our experimental probability, again, let's write this down here. Experimental probability is a number, again, that's based off of your experiment. In this case, experimental probability, 17 over 50 represents a win. Okay, so again, 17 over 50, let's figure that out. Is it going to be, think about, well, yeah, it's 34%. Right? 17 divided by 50 gives us roughly 0.34 or 34%. So I can use this percentage now as my expected value. Okay, or in other words, in these 17 times, I won $3. Okay, and in the other 33 times, I won nothing. Okay, yet in all 50 times, I spent $1. Okay, so let's say out of my pocket is 50, and in my pocket is 17 times 3. Okay, that's another way to think about it. Okay, so again, 17 times I won $3. So we'll say the expected value is equal to 0.34 times $3 plus, and then the probability I'm going to lose is just the difference. So 33 out of 50 gives me 66%, and I win $0. And you'll notice I should get a pretty similar result to 95 cents. So 0.34 times 3, and I get $1 too. Okay, again, pretty darn close to 95 cents. On a quiz, on a test, on a final exam, I would accept either answer. Okay, and then analyze these two answers. Okay, if I look at this closely, I mean they're close, but would you say that I was lucky or unlucky in those 50 trials? Okay, I would say I was lucky. Okay, why? Because the experimental expected value outweighed the theoretical expected value. But more importantly, my expected value outweighs the buy-in, right? I'm spending $1 each time. So what this is saying is that in those 50 counts or in those 50 trials, every time I spend $1, I win 2 cents. Win 2 cents. Now, think about that. That's me being very lucky. If I try and take that statement, and broadcast that to every single time anybody plays roulette in the casino, once word gets out about that, the casino will fold, right? It'll go belly up because think about it. I would be playing more than $1 every single spin. I'd be paying $1,000 if I'm going to win 2 cents to every time I play this for $1. That's a great investment on my part, kind of like a savings account, in a way. So that's a quick discussion there on expected value and the similarities that it has with simulation.